The first step in making a MOSFET is to dope the silicon wafer to create a source and drain area. However, to achieve this, we first need to make a silicon oxide mask which will protect the rest of the wafer from being doped. This video covers the process needed to make the silicon oxide mask. It is important that you pay close attention because some of this work will be completed by you in the lab. The first step is to grow the oxide on a silicon wafer. Then, photolithography is used to create the mask pattern on the wafer. Next, the mask is created by etching away the oxide layer not covered by the photoresist. Finally, the photoresist is removed and the pattern oxide mask is then cleaned. Before growing the silicon oxide, the silicon wafers need to be cleaned. The first step in every thermal process of the wafer is an RCA clean to remove contamination before it can be baked into the wafer. Here, your lab instructor Bahare is cleaning the wafers in a heated RCA solution. Hydrogen peroxide is then added to the solution. After about 20 minutes in the RCA solution, deionized water, or DI water, is slowly added to dilute and cool the solution. The wafers are then carefully washed with DI water and then dried with clean dry air. With all the wafers clean, they are ready to be put in the furnace to grow the oxide layer. A quartz boat is used to hold the wafers so they can be inserted into the furnace. The quartz boat is then moved into the tube furnace. Here, the wafers will be heated to 1050 degrees Celsius for 5 hours in an oxygen environment to facilitate dry oxide growth. After the wafers cool over approximately 4 hours, they are ready to be removed from the furnace. The gold color indicates there is approximately 200 nanometers of oxide on the wafer, which is ideal for fabricating the required oxide mask. These time-consuming steps will be completed for you by the lab instructor before you come into the lab. Photolithography is used to add the patterns of photoresist to the wafer, which are required before the oxide layer can be etched. With the silicon wafer firmly mounted to the chuck of the spinner, hexamethyldisilazane, or HMDS, is first applied to the wafer. Once applied, the wafer is spun up to 5000 RPM to ensure a thin, uniform coating is left on the surface. The HMDS acts as an adhesion promoter for the photoresist, which will be applied in the next step. The wafer is then baked at 150 degrees Celsius for 3 minutes to set the HMDS. A cleaning process of washing with isopropyl alcohol, then acetone, then DI water is used to prepare the wafer for the photoresist. The wafer is carefully dried and then placed back onto the spinner. Photoresist is applied to the wafer so the whole surface is covered. The spinner is turned on and the photoresist is shed from the wafer as it spins at 500 RPM for about 10 seconds. Then, the wafer is spun up to 5000 RPM for another 60 seconds to ensure that a thin, uniform coat of photoresist is left on the surface. The wafer is then set on a heater to pre-bake at 110 degrees Celsius for 2 minutes with vacuum applied. Next, the wafer is moved into the mask aligner to expose the mask 1 pattern onto the photoresist using UV light for 240 seconds. The wafer is then moved back to the heater for a 2-minute post-bake with vacuum applied. Next, the wafer is dipped in the developer for around a minute to develop the pattern on the wafer. The wafer is carefully washed in DI water to stop the development from proceeding. Once the wafer has been washed and dried, it is checked under the microscope to ensure the photoresist is good. If not, the lithography steps will have to be redone. This wafer is good, so it goes back on the heater again at 110 degrees with the vacuum applied for a 2-minute hard bake, which completes the photolithography process. The next step is to etch the silicon oxide layer using hydrofluoric acid. This will remove all the silicon oxide that is not covered by the photoresist pattern. Hydrofluoric acid poses a health hazard to those working with it. In the case of accidental splashes, proper personal protective equipment must be worn, such as heavy gloves and a face shield, to ensure no contact with eyes, face, or skin is possible. It is also important to note the silicon oxide removed by hydrofluoric acid is essentially glass. Therefore, glass beakers cannot be used in this process, as they will also react with the hydrofluoric acid. The processed wafer is placed in a holder so it can be safely dipped in the hydrofluoric acid solution. The wafer is dipped in the HF and a timer is started to verify the etch rate, which can predict when the etching will be complete. The etching is stopped by dipping the wafer into deionized water. The quality of the etch is checked by slowly removing the wafer from the buffered HF or water while checking for hydrophobic or hydrophilic behavior. The bare silicon that is exposed after the silicon oxide is removed is hydrophobic. When the liquid beads away completely from the exposed surface, this is a good indication the silicon oxide is completely removed. The wafer is then washed and dried and the resistance is checked. If there is an oxide layer on the wafer, the resistance seen by the meter is infinite. Resistance in the kilo-ohm range indicates the oxide layer has been removed and the silicon is bare. Finally, the wafer is washed with acetone to rinse off the remaining photoresist, and it is now ready for doping. This concludes the video on oxide mask creation. Please join us for the next video, which covers the wafer doping process.